Hi folks, my segment 3 crashed on me, so I couldn't do more than 8 minutes. But anyway, we're starting from where we left off, and if you go back to the figure that I had before, and in fact I may have it down here too. Yeah, I did draw it here. This is repeated. This is zero. It's sum of all the forces applied at node number 4 coming from both elements. Now, all right, let's go put all this information together in the matrix that I have down here. So we have here 0, M2, M3, M4, 0, K1, minus K1, minus K1, K1 plus K2, minus K2, minus K2, K2 plus K3, minus K3, minus K3, K3 plus K4, minus K4, minus K4, and K4. And on the right side, you have a unknown reaction force at the wall, left wall, applied external force F, which can be, by the way, these are all functions of T. These are all functions of T. 0, 0, and R5, which is also a function of T. So this is called the global. This is called the global equation of motion. And notice that it is a 5 by 5 system. All right. I don't know whether this is recording or not, but anyway, let's give it a try. And this is the, let me write it here. It's the global equations of motion. Incidentally, notice that this is 0, this is 0, this is 0, and this is 0, and 0. One can, ignoring the first and the last row of the system, we can write it in this form: M2, M3, M4, X1 double dot, X2 double dot, X3 double dot, X4 double dot. This is the reduced mass matrix, plus that'll be K1 plus K2, minus K2, minus K2, K2 plus K3, minus K3, uh, minus K3, and K3 plus K4. This is times X2, X3, X4 equal to F0, 0. This is the reduced equations of motion. All right, now notice that this thing is the reduced mass matrix. It's called reduced mass matrix. And this guy is the reduced stiffness matrix. Okay. There are certain things that you can see in these matrices. First of all, both are symmetric. Remember also the element mass matrix and element stiffness matrix, which were 2 by 2, were also symmetric. And they're banded, or let's call it sparse. Sparse means that it has a lot of zeros. Now you cannot see a lot of zeros here, but keep in mind that if we had more spring elements, then the size of these matrices will be bigger, and you see a lot more zeros. You can see it's called banded because everything goes along this band, and lots of zeros outside of that band. Same thing down here, of course. And these are the properties of systems which are linear elastic. The mass matrix and the stiffness matrix are going to be symmetric and sparse. Now, of course, in the case of the 3D geometries, these matrices are huge. For example, if you look at the tetrahedral element that exists in CATIA, for example, the linear tetrahedral element, each node has 3 degrees of freedom. In other words, displacement in U, displacement in V, displacement in W. So there are, in this particular element, there are 4 nodes, each 3 degrees of freedom. So the element matrices, element mass matrix is 12 by 12. Element stiffness matrix also is also 12 by 12. If you are dealing with, let's see, if you're dealing with a parabolic element, which looks kind of the same, except that there are intermediate nodes. There are 10 nodes. Each node having 3 degrees of freedom. So there are 10 nodes, each 3 degrees of freedom. So mass matrix is 10, let's see that, that means that there is a total of, let's see, is that 10, by the way, 10, yeah, let's see now, how many nodes do you have here? There's 6 here, 10, yeah, that's right. Each mass matrix is, the total number of degrees of freedom is 10 nodes, each one 3 degrees of freedom, that is 30. The mass matrix is 30 by 30. And stiffness matrix is also 30 by 30. Lots of zeros, symmetric. Okay. I'm going to stop this video here because I'm not quite sure whether this is recording. So let me stop this.